Part 4. The Design Solution. Investigation. Architectural solutions have been investigated through research, analysis, exploring precedents, conceptualization, and refinement. The vertical farm and the zeitgeist movement defined are the two primary driving texts for the design logic, providing useful guides on clarifying and addressing the aforementioned crises as follows. A crisis summary. Fossil fuel dependent agriculture will be addressed by reducing food mileage by distributing where grown, reducing the need for disposable packaging, and minimizing storage duration. Eutrophication and pollution will be addressed by eliminating the need for fertilizers, pesticides, and agricultural runoff. Topsoil erosion will be addressed by using soilless farming methods. Water use will be addressed by capturing and reusing water in a closed system. Land use will be addressed by the fact that vertical farming is 10 times more land efficient than conventional farming. Wastage will be addressed by using enclosed crops that are not as susceptible to pests or weather conditions. Perpetual human employment will be addressed by using automated systems to replace traditional human roles as much as possible in order to improve productivity and demonstrate that the required value shift from labor to income to maximizing technical efficiency. Conceptual precedents. Initial design rationale. Many conceptual precedents were analysed during the initial stage of this project, which undertook many different stages. What stood out was the basic shape of the towers of these buildings. Cylindrical towers allow for maximum sunlight penetration for crops, as well as rotary systems for crop harvesting, watering, and so on. This basic shape is conducive for high-capacity production using low-tech methods, and later this changed to accommodate only high-tech organic production and low-capacity production. Physical precedents. Existing vertical farms were somewhat limited to low-tech solutions from what I could find. This led to a high level of required exploration through trial and error to create a new architectural typology, not only dedicated to optimizing crop production, but doing so through the use of automated systems using existing conceptual design components. Existing automated farm systems. The initial design concepts accommodated existing automated vertical farm technologies, while allowing for alternative methods for research and innovation. The final design was designed explicitly for vertical farm Australia fittings once the project was scaled down. These fittings require insulated walls, but do not require sunlight. Existing programmable Autobots. The architecture has been designed to accommodate Baxter Autobots to be used in conjunction / replace human labor in the kitchen areas of the building as a practical and demonstrative building component. Bionic handling assistance. The use of an existing technology named the Bionic Handling Assistant was considered for architectural integration because of its handling sensitivity for organic produce. This was later phased out and not used. Automated construction techniques. Existing and conceptual automated construction processes were considered in the early stages of this project. This provided opportunity to consider what a structure may look like once the limitations of manual construction have been eroded, providing opportunities for organic, porous structures. This idea was later deemed too conceptual for the design brief and put aside for a more traditional structure. Site analysis. The site location is very exposed to direct sunlight. This should be addressed through design with shading devices and trees. The adjacent Parliament House has an interesting threshold space that should be approached with sensitivity. Pedestrian traffic. The existing pedestrian overpass may not be sufficient for new users circulating from the new Adelaide Oval footbridge. A more diverse circulation design will be considered. Landscape potentials. The existing site has an indoor car park on the lower ground level that allows for vehicle access and pedestrian roof that is flush with the Festival Centre pedestrian roof. This can somewhat be maintained to allow for vehicle access to the automated vertical farm, import-export area, and to allow an extension of the pedestrian overpass. There are many public transport waiting zones in the nearby proximity that can be provided with further shelter and amenities. Existing design concepts were also analysed for their proposed landscape solutions. Broken shade. A porous 3D printed structure was conceptualized for the primary purpose of natural broken shading and as a potential surface for organic growth as an auxiliary or optional use. Internal tower. The internal structural tower was designed for versatile high-volume production with associated consumption areas including a fruit and vegetable market, food court, and rooftop dining. The height of the 13-storey building was determined by current government-approved zoning regulations, allowing for 20 stories on the plaza, remaining prudent for the large-scale ceiling spans. The internal core and outer ring change according to the specific function of the floor level in this building. For example, storage, production, quality control, etc. The farming floors have been designed to accommodate a modular automated conveyor and food elevator system. This allows versatility within a restricted structural grid to accommodate the various requirements of vertical farming, while allowing for efficient automated transportation of produce through various sectors of the building. Shown on the left is the design in its entirety, showing the maximum options available for the inner core. When purchased as an online product, customers can choose to arrange the inner core by choosing from a selection of pre-designed floor options. Or they can be custom designed by the customer or professional designer on a per-case basis. The exterior ring of the farm plan allows for a variation of farming techniques to be experimented with, allowing for versatility, research, and diversity in produce. Schematic overhaul. A quarantine floor with many showers, facilities, a cinema, and auxiliary learning space was included to promote awareness and maintain sterility so that produce can remain pesticide-free. Unfortunately, this design scheme was rejected by the university due to problems including a circular structure creating unnecessary limitations and introversion. The building was deemed too tall for this context. It was too conceptual. High volume production was not suitable for the city context, and too large in the plan for the context of the surroundings, causing poor relationship with the buildings surrounding it. These variables were taken into consideration in the following design. So the single use of vertical farming was also deemed to be a major issue for the city context, with the idea of a multi-purpose, highly versatile commercial building being agreed upon while maintaining fragments of the original ethos of food production. Phase 2 of the design included a reworking of program to accommodate the Coral design brief. It changed from a typical production-based vertical farm that was deemed unsuitable to the city context to a highly diverse commercial program, potentially more suitable for a city context. This image represents the brainstorming to figure out the diverse range of programs including saunas, spas, cinema, gardens, pools, fitness centres and more, as a rehabilitative response to the surrounding degenerative cultural norms, while maintaining the initial food production and automation elements. The following redesign was based on teachers' feedback, as well as my own initiative to include a smaller scale building with a more diverse program, using a rectangular shape to allow for more efficient organization and diversity of floor plans, while scaling back the idea of the 3D printed shading devices to a minimum as suggested. This included a rooftop restaurant overlooking the Torrens, food production and distribution, and relaxing rehabilitation amenities in the lower ground level. The food elevator core and integrated automated components were explored through a large-scale section and working physical model. This allowed a level of refinement for the automated kitchen and automated modular storage shelves for selling raw produce with minimal human labour. It became evident that the conveyors must use the racks as a support network and use internal organisation opposed to external safety, so the bionic handling grips were removed from the design in the later stages. Other changes, according to the teacher feedback, included further resizing of the building to allow pedestrian circulation around all sides of the building, and program reduction in order to allow a shorter building with less program diversity, as apparently the building had become too diverse for the context and scope of this project. This involved a complete redesign of the building again, while maintaining the basic shape and column grid. Changes from this submission included making the windows match the surrounding buildings and changing the roof to a more simple form because it was deemed too large, wavy, and overbearing.